Lately, I've been working on graphing your quadratic functions, whether they were in factored form or vertex form, and our focus has been vertex form. So we're going to look through 3 examples together, again, about graphing things in vertex form. And then our next couple of lessons will be practicing graphing both factored form and vertex form together, and then you'll have an upcoming assessment. So we take a look at number 1. We want to graph this function and identify the key features. So again, we always say, look at the function and see what form it's written in. This is our vertex form, right? The transformation format. And we look at the equation, and remember the parent function is x squared. I can see 2 transformations here. I can see the x minus 5, and I can also see the minus 4. The x minus 5 is saying, hey, I'm moving 5 units to the right. The minus 4 means I'm going down 4 units. Therefore, it's telling me the location of the vertex has to be at 5, negative 4. So I plot that on my graph. I put it in the center of my table. Now, what I can do, a couple things at this point here. Because I know where the vertex is, we have talked about how the mirror, the axis of symmetry, is going through that vertex. So I could draw in my mirror, my axis of symmetry right here at x equals 5. And that would help me build my table around it. Now, if you want to hold off on that stuff, excuse me, and do it a little bit later, you can. It's up to you, but we've talked about these things before. And again, your axis of symmetry, the equation, we said is going to be x equals 5. So when we go to our table, we are going to build around 5. So I'm thinking about numbers to the left of 5. That could be 4, 3, 2, 1. Going to the right of 5, that would be 6, 7, 8. You are picking the values. You are making that determination. So whatever you are picking, remember, you are selecting those values, and you're going to take them and substitute them in for x into the original equation. So I could put 3 in for x. I could also put the 4 in for x. And just do some calculations. So if you had a calculator, you could type it in exactly how you see it, press enter, and you'd have the y value. We only really have to do 2 of these calculations because of that mirror image, right? Your axis of symmetry, whatever I have on the left would be reflected on the right. So our values ended up being 0, negative 3, and here's its match, negative 3, 0. So I've got my points plotted. I can see the starting of the curve of the parabola. I can connect them. And I can see a couple of things going on. So to recap, we said the vertex was at 5, negative 4. X-intercepts where crosses the axis right here. I can see them. I also can see it in my table where the output, the y, is 0. So I have x-intercepts at 3, 0, and 7, 0. Now the y-intercept, that's where it's going to cross the y-axis. And this little window I have here, I can't see it, but I know y-intercepts always have an input of 0. So what I'm going to do is I'm going to pause here and take 0 and put it into my equation to see what I get out. Excuse me. So if I do 0 minus 5, that's negative 5. Negative 5 times negative 5, because I'm squaring it, that's 25. 25 minus 4, well, that's going to be 21. So my y-intercept will be at 0, 21. We talked about before the mirror image here, the x symmetry, x equals 5. We know the domain for our function is always the same for every quadratic, negative infinity to positive infinity, no restrictions. And the range is a different story. Again, we're going from lowest to highest. Our lowest y value here happens at the vertex, so that's at negative 4. You can see it in your table as being the lowest y value. Now, what's the highest it can go? Well, because it's increasing, because we see the concavity is up, that is going to go to positive infinity. So I can finish my notation for those 2 things. I've got a bracket around the negative 4, parentheses around my infinity, and I got my concave up. Now, if we look at number 2, again, it's already written into vertex form. We want to think about the transformations going on to help with the graph. Based on those transformations, we're going to be able to tell the vertex, axis symmetry, we might even be able to tell concavity. It just depends on what we see. And again, it's always compared to x squared. So if I look at my equation, I see 1, 2, 3 changes from the original. The negative in the front means it's going to be reflected over the x-axis, so my concavity is down. The +3 tells me that's going to the left 3 units. The -1 is telling me that I am going down 1 unit. So if I'm going left 3 and down 1, that means my vertex is at -3, -1. So if my scale is 1, and forgive me, I forgot to write my numbers here, so let me add that in quickly. We have our vertex in our graph. And we're going to build our table around where that vertex is. So I want numbers to the left of -3, so that would be -4, -5, -6. I want the numbers to the right of -3, so -2, -1, 0 even, because that would tell me my y-intercept. Because the vertex is here, another thing you could do is you could sketch in your axis of symmetry here at x equals -3, reminding you what you see on the left is the same as the right. So if we do a quick substitution, any of the values that we pick for x, and we're putting them into our pattern, remember you've got that -1 here, you're going to put that -1 in front of all of those patterns, and you're going to type this into your calculator and see what you get out. If you want to simplify it in your head, you're more than welcome to. But this will give you the values for your parabola. And as we're going through and checking, remember here's that axis of symmetry at x equals -3. We see the mirror image, the symmetry in the table around the vertex. So here's my data points. Excuse me. If you use a -6, that mirror image is here at 0, so it happens to be your y-intercept. And so we have that y-intercept at 0, -10. We have the axis symmetry that we talked about, -3. We know it's concave down. Because we moved it away, down from the x-axis, we have no x-intercept, so you want to make sure you're writing none for that. That leaves us with the domain and range, and we know every quadratic function, the domain is all real numbers, -infinity to positive infinity, that's always inside your parentheses. And again, it's going from lowest to highest, so that means left to right for the domain with the x's. Range, lowest to highest would be how far down to how far up. Now this we have to be careful of because it's concave down. We know it's going to keep decreasing, so there's no limit to how far it can go. So I need to start with -infinity here. And I do have a limitation with how high. I can't go past -1. And I can see that in my table. I can see that in my graph. So my notation would be parentheses -infinity, comma, -1 with a bracket, because that's my limitation. I cannot go past that -1. All right, we've got one more. Number 7. So again, this is already in our vertex transformation format. So we're going to think about the movement. So we can get the vertex, we can think about the concavity, the axis symmetry, build around the vertex in my table to get my graph, and then talk about the key features. As I'm looking at my equation, I see 1, 2, 3 changes from what I would compare it to x squared. This 2 means it's 2 times faster than it was before, so I'm anticipating it being narrower. Also, since it's positive, I know it has to be concave up. Now here, as I move to the x -4, That's going to tell me how I'm moving left or right. Because it's minus, I'm going to the right 4 units. And here, this minus 8 is telling me I'm going down 8 units. So I have all of my transformations, right? Here's my vertex, 4, -8. Here it is on my table. Excuse me. If we know the vertex, we also know the axis of symmetry, which we could sketch it now, or you could hold off later. That would be x equals 4. And the concavity, we said since that a value, the leading coefficient here is a positive, we know it should be concave up. Now, I need to pick values in my table to build around the vertex. So I'm going to pick numbers to the left of 4. So that would be like 3, 2, 1, 0, so I can get the y-intercept. Then I need numbers to the right of 4, so like 5, 6, 7. All I have to do is take a couple of these inputs, substitute them into the original equation to see what I get out. Again, you can type that exactly the way you see it into your calculator, or you're welcome to do the simplification process in your head. But remember, because we have the vertex, your axis of symmetry, we should see a mirror image appear in your table. Now, we can tell for the x-intercepts where they are based on my graph and also in my table, because x-intercepts have outputs of 0. So they're located at 2, 0, and 6, 0. My y-intercept is not in the table, but we know it has a 0 for the input. And I know it's going to happen someplace up here. We're just going to do a quick calculation. So I put 0 in for x, just like you did for the other ones here, and do my calculation. That ends up being, excuse me, 24. We talked about the axis symmetry, and again, you probably drew that in back towards one of your first steps. The domain never changes, negative infinity to positive infinity. We already talked about how it's concave up, and so the range, we're going lowest to highest. So the lowest is that y value from the vertex, -8. Concave up means it's never going to stop, so we've got to have that positive infinity. So at this point, it's your turn to practice. They have you select 5 of the remaining graphing problems to do, and then we'll review your work during the next lesson.